Hi, in today's video I'm going to look at a very interesting problem from International Mathematical Olympiad from 1999, question number 3. Okay, determine all integer n greater than 1 such that to the n plus 1 over n squared is a natural number. Okay, this problem is a part of fundamental arithmetic and number theories theorem. Okay, so you can give the hint before we start solving this problem. You can give hints to this problem. Always start with the small numbers, which can help you. You may have the first solution or something. And then the second thing, before we start solving this problem, you can give hints to this problem. Okay, by trying the first obvious cases. Okay, you can try for the n equal to 1 first to see you may have solution in the first order. Okay, second thing, we are going to use very important and useful theorem for the which is modular theorem. Okay, the modular theorem, it says if p is a prime and p not divide a, then a to the p minus 1 congruent to the 1 mod p. There is a Bezout theorem. Okay, for m n are the natural number, there is some x and y such that mx plus ny equal to GCD mn. In the other word, GCD is that two numbers are written on the linear combination. Okay, let's start solving this problem. So we have 2 to the n plus 1 over n squared is a natural number. Okay, I'm going to start. Let's start with the first order, n equal to. So this implies 2 to the 2 plus 1 over 2 squared, which is 2 to the 4 is 5 over 4. This is not the natural number. Okay, so the n equal to 2 is not solution. Let's start with, for all natural number, n is greater than 2. Okay, so we have 2 to the n as a condition. To the n plus 1 over n squared is a natural number. That's mean n squared divide to the n plus 1. Okay, to the n is an even number, even. Okay, implies to the n plus 1 is an odd number. Okay, since n to the 2 divide to the n plus 1, this one, that's mean n squared is an odd number as well, because even number never ever divide the odd number. Okay, so n squared is an odd number. Okay, implies n is an odd number as well. So for all n greater than 2, okay, let p to be the smallest prime such that p divide n. Okay, so since n is an odd number, p is a prime. Okay, both of them are odd numbers because n strictly superior than 2. That's mean p is also strictly superior than 2. Okay, that's mean at some points p as a prime can divide n. Okay, so what does mean? That's mean p divide n square as well, because n is a multiple of p. Okay, since we have two conditions, since we have n squared divide to the n plus 1, okay, and also p divide n squared, what this mean? P divide to the n plus 1 as well. This is transitivity type property of divisibility. Okay, this one is equivalent to the divisibility statement. Okay, So this means 2 to the n plus 1 congruent to the 0 module p. Okay, let's bring this one at the top and continue. So we have for all n greater than 2. Also we have p divide n. So since we get here, okay, so as you know, to the n plus 1 over n squared is a natural number. For all n strictly superior than 2, we have p divide n, p as a prime number, n is an integer. We have this equation as we have now, to the n plus 1 congruent to the 0 module p. Okay, mean to the n plus 1 is a congruent to the 0 mod p. Okay, so equivalent 2 to the n congruent to minus 1 mod p. Okay, this one, what this mean? This one, since we have p divided to n, we have to have 0 here. Okay, to the n congruent to the 0 mod p in order to have p divide to n, but we have minus 1 here. That's mean p not divide to the n. What does mean? This mean we are going to this one. That's mean this one is verified the modular theorem. Okay, what the modular theorem says? If p is a prime, so p is a prime in this case. Okay, this condition is verified the modular theorem. Okay, what's the modular theorem says? If p is a prime number and p not divide a, as we have here, p is a prime, not divide this natural number which is 2 to the n, then a to the p minus 1 congruent to the 1 mod p. Same thing here. So a is a 2 to the n, so this one implies 2 to the n exponent p minus 1 as a prime number congruent to the 1, okay, mod p. Alright, so now I can raise n as an exponent. I can make some simplification here. This one is 2, that's mean 2 to the n by 2 to the n p minus 2 to the n p multiply p minus 1 congruent to the 1 mod p. Same thing if I write 2 to the p minus 1, 2 to the n. Okay, so congruent to the 1 mod p. Alright, I can take n off from exponent because we have 1. This one is the same thing if I put 2 to the p minus 1 congruent 1 mod p. Okay, so as you see here, we have two equations. We have 2 to the n congruent to the minus 1 mod p. Okay, so this is very important equations. Implies p minus 1 not divide n, because p is a prime as an odd number, p minus 1 is an even number. So even number never ever divide odd number, because n is an odd number. N is an odd, as we mentioned before. Okay, so what does this mean? This one is a verified Bayes' theorem. Okay, so what does this mean? P minus 1 not divide n. That's mean GCD to the n p minus 1, okay, equal to 1. Okay, so this one is a verified Bayes' theorem. What's the Bayes' theorem says? For all natural number mn, there is x and y are the integers, okay, such that mx plus ny equal to GCD. Okay, because this is without loss of generality. You have to have the natural number. It can be positive, x and y. It could be positive, it could be negative. Okay. So, but mn are the natural number, has to be positive. But I can take the special case of the basic theorem by putting x and y are integers, are the positive numbers. Okay. I will show you now. So now I will explain to you 1 second. So this x and y are the integers number. Okay, such that n to the x minus y, p minus y 1 equal to 1. Okay, since I have minus sign, so this one I change it, x and y, I change it to the natural number. I'm pushing minus sign inside of this one because I want x and y be positive numbers. Okay, that's why I'm putting x, y are the integer numbers. So I'm taking the special case of this basic theorem. Okay, without loss of generality, there is x and y are integers. It could be positive, it could be negative. Multiply by 1. Okay, equal to, I'm going to replace number 1 by this one. Okay, by this equation. So I will have 2 to the p minus 1. Okay, to p minus 1. I'm erasing also 2 multiply by 1 equal to 2. I'm going to replace number 2. I'm going to replace number 1 by this one. So 2 to the p minus 1. Okay, so this one is a congruent, not equal sign. Okay, so I'm going to erase number 1 y, also I'm erasing y here. I'm multiplying number 2 on both sides. Okay, I'm multiplying number 2 on both sides. So now this one will be modular of p all the way down. Okay, to simplify a little bit here, so this one, as you see, the y is an exponent. I'm going to bring the y here, and with 2 outside will become 2 to the 1 plus y multiplied by p minus 1. Okay, we have this one. This one is a congruent. As you see here, I'm going to replace this combination linear theorem of Bayes into here. As you see here, I'm pushing nx to the other side. So will nx equal to y, p minus 1 plus 1. Okay, as you see here, I'm going to replace this one here. Okay, so I will have I will have 2 to the nx congruent. Also I'm putting to the n, also I'm putting x as an exponent. So to the n equal to this one, minus 1, as you see it here. I'm replacing minus 1 into here, minus 1 to the x. Now we don't know x is an odd number or even number. As you see here, 1 is an odd number. As you see here, p is an odd number, but p minus 1 is an even number. So in order to have odd number, you have to have odd number minus even number gives you odd number. So that's this one. Since we have n is an odd number, x must be odd number as well. Y is an even number. Okay. Since we have x is an odd number, so doesn't affect this minus sign of minus 1. I'm going to take x off from exponent, so I will have minus 1 mod p. So if you take a look at here, this one all the way down, I have number 2, okay, congruent to minus 1 mod p, right? This one equivalent 2 plus 1 this one equivalent, this one equivalent. I'm bringing -1 to the other side. I will have 3 congruent to the 0 mod p. Okay, what does mean? This one is equivalent to the divisibility statement. Okay, this one p, this means p divide 3. Okay, this is what we get from the previous step. We have 3 congruent to the 0 mod p. This one is equivalent to the divisibility statement. Okay, that means p divide 3. Okay, we found p divide 3, and also in the earlier, also we have p divide n. P is a prime number, and p is a prime number, and also n is an odd number. So since p divide 3, so this one will be happen if p equal to n equal to 3. Okay, so now thus there is only one solution, which is n equal to 3. Okay, this is the good place where you can stop. Thank you for watching. I will see you in next video. Bye.